Chapter 7: Gases, Liquids, Solids, and Phase Diagrams. Section 7.2: Compression Factor. The compression factor Z of a gas is defined as this: Z equals PV over nRT, and PV over nRT is pressure times molar volume over RT. For ideal gases, Z equals 1 because PV equals nRT for all ideal gases. For a van der Waals gas, we need to use the van der Waals equation for pressure here. We will assume the molar volume of a van der Waals gas is much greater than the parameter B when we do some derivations for the expression of Z. Now let's do this derivation here. The compression factor is P times molar volume over RT. For van der Waals gas, the pressure is RT over molar volume minus B, and then we subtract A over molar volume squared, and then multiply by molar volume. There are two terms. The first term is this because RT and RT cancel. We have molar volume over molar volume minus B. And over here we have RT on the bottom, and then it becomes A over RT molar volume. This is because this molar volume and this molar volume squared partially cancel. So we have this equation. And if we divide both top and the bottom by molar volume, this becomes 1 over 1 minus B over molar volume, and then subtract A over RT molar volume. So over here, 1 over 1 minus a small number is approximately 1 plus that small number. Over here we have a mathematical equation. So 1 over 1 minus delta, we can expand it to 1 plus delta squared plus delta cubed, etc. when delta is small. And if delta is much smaller than 1, delta squared and delta cubed are much smaller than delta. Therefore, we can approximately say 1 over 1 minus delta is equal to 1 plus delta. Therefore, this term is approximately 1 plus B over Vm. So Z is 1 plus B over Vm minus A over RT over Vm. And 1 over Vm is a common factor of the last two terms. Therefore, the compression factor Z of a van der Waals gas is roughly 1 plus the reciprocal of molar volume multiplied by B minus A over RT. You can see this B is the repulsion term in the van der Waals equation. A is the attraction term in the van der Waals equation. And also we can easily analyze this compression factor Z for a van der Waals gas. It's just because if B is greater than A over RT, we have Z greater than 1. If B is smaller than A over RT, then Z is less than 1. When Z is greater than 1, its pressure is greater than nRT over V. nRT over V is the pressure as if the gas were ideal. And if Z is less than 1, then P is less than nRT over V. nRT over V is the pressure of the gas if it were ideal. If we have a temperature right at A over BR, so we can plug this temperature here, A over BR, and then we'll have B minus A over here, this is A divided by B on the bottom, and then we get actually B minus B. Z is equal to 1. So in this scenario, Z is equal to 1 when the temperature of the van der Waals gas is equal to A over BR. And this temperature is called the boil temperature. So at the boil temperature, PV is equal to nRT because of the cancellation between the attractive effect and the repulsive effect in the van der Waals equation. Again, the compression factor Z of a gas is defined as follows. The lowercase z is equal to PV over nRT, or pressure times molar volume over RT. For ideal gases, the compression factor Z is simply 1. For a van der Waals gas, Z is approximately 1 plus. Over here we have the reciprocal of molar volume multiplied by the difference between B and A over RT. Again, if B is greater than A over RT, Z is larger than 1. If B is smaller than A over RT, Z is less than 1. That's why we sometimes say when the repulsive force is predominant, Z is greater than 1, PV is greater than nRT. When the attractive force between the real gas particles is predominant, we have Z is less than 1. The compression factor is less than 1, PV is less than nRT. And over here we have the compression factor Z of a nitrogen gas versus pressure. So you can see there are 4 lines. They're at different temperatures: 220 Kelvin, 273 Kelvin, that's just 0 degrees Celsius, and we have 327 Kelvin, which is roughly 54 degrees Celsius, and then 400 Kelvin, which is roughly 127 degrees Celsius. So you can see Z is actually a function of pressure with a different pressure. You have different Z values. It's also a function of temperature. You can see, we have 4 different temperatures, and we have 4 different curves of Z with respect to pressure. So even if we have the same pressure, for example 100 bars, we have 4 different values for Z. These 2 are below 1, these 2 are above 1. Now let's look at the temperature effect. When temperature is really high, for example in this case we have 400 Kelvin. When temperature is really high, well, this term is usually small, and B is usually larger than A over RT. Therefore Z is usually greater than 1. As we can see, at 400 Kelvin, Z is greater than 1. Even at 327 Kelvin, Z is also greater than 1. If the temperature is lower, if we look at this, when temperature is lower, this A over RT can be competitive with B. For example, let's look at the green curve. So over here at around 140 bars, well, these B value and A over RT are about the same at this 0 degrees Celsius or 207.3 Kelvin. So over here at around 230 bars, you can see this blue curve is taken at 220 Kelvin. So at 220 Kelvin, roughly this B is equal to A over RT. Approximately, for 2 reasons. One, the van der Waals equation is not exact. Number 2, even this is based on some approximation we made before. Remember we assumed this molar volume is much greater than B, and then we get this equation. However, at a very high pressure, for example around this region, 100-200 bars region, Vm may not be much greater than B. Vm might be several times larger than B, but not much larger than B. So over here, this I think this graph is based on the real experimental data for nitrogen gas. This is based on the van der Waals equation, and based on the assumption this molar volume is much greater than B. So these 2 do not match exactly, but still we can have a rough understanding here. If temperature is really high, then the repulsive force is predominant. Z is greater than 1, and only when T is low enough, then it's possible for these 2 terms cancel each other. So at this boil temperature, when temperature is equal to A over BR, Z is approximately 1. So over here Z is approximately 1 here, Z is approximately 1 here.